Last week we collected a lab in which you try to verify the law of conservation of momentum in one dimension. It looked something like this, if you remember it. We had object number 1 moving at a certain speed towards a stationary object number 2. They collided, and then after the collision, they stuck together and headed off as one object. Okay, we found the initial velocity of object number 1, the final velocity of the combined mass. We ended up plotting a graph and then determining whether the law of conservation of momentum was valid based on that graph. Today, you're going to do an activity where you're going to try to verify the law of conservation of momentum in 2 dimensions. So what would the problem be for this one? What is the law, is the law of conservation of momentum in 2 dimensions valid? Or you could say, is momentum conserved in a 2-dimensional collision, or something to that effect? Basically, is 2-dimensional conservation of momentum true? Is what I taught you the truth? Today's lab is going to look something like this. You're going to fire one object, which is going to be a baseball, at another object, which is going to be a baseball, at an angle. Now, I've got them drawn at 90 degrees here, but you could just as easily fire them like this, as a glancing collision. The bottom line is you want them to collide at a certain point, and then you want them to head off as separate objects after that collision. So if you have it the way that I have it drawn first, it's going to look something like this probably. If the collision point is like this in the second diagram, it's going to look more like this. It doesn't matter. They don't have to be 90-degree angles. Makes life a tiny bit easier for you if they are, but it's going to be pretty difficult for you to ensure that they are 90-degree angles. If it works out that way, great. If it doesn't, oh well, it's not a big deal. Now, how are we going to record the velocities, both initial and final, of these objects when we can't use a motion sensor? We can't use a motion sensor we used for the last activity because it doesn't distinguish between X and Y. It could tell me how fast object number 1 is moving, but it can't tell me what's X component, what's Y component, nor can it tell me what the angle is. In addition, I can't use 2 motion sensors at once, so if I've got 2 objects moving at the same time, that's a problem in using the motion sensors. So here's what you're going to do today as a group. You're going to record this with your phone. You're going to use a video camera to record this from above. Now, you're probably not going to be able to record it directly above because you want to have that phone steady. And if you're holding it in your hands directly above this collision that's taking place on the floor, it's going to shake a little bit like this, right? So you're going to have to brace it somehow. Maybe put it on the edge of your desk. A couple of groups went out to the atrium and videoed the baseballs moving on the floor of the atrium from the bridge of the atrium, which gave them a really, really big field of view. Okay, whatever works for you. Our biolab is open, the classroom is open, and the atrium is open as well. Again, whatever works for you. Video it as close as possible to from above. If you video it from an angle, you get what's called parallax error. Parallax error occurs when you're trying to take a measurement from an angle and you get a false measurement because of that. It occurs every day if you sit in the passenger seat of a car. You look over to the speedometer and you think you're going a certain speed. The driver says, no, I'm not going that speed, because it looks to you from the passenger seat as if you're going a slightly different speed because you're viewing the speedometer from an angle. If we put the camera not directly above, we get the same parallax error as we do when we're sitting in the passenger seat of a car. Now, you may not be able to put it directly above, put it as close to overhead as possible, but while keeping it steady at the same time. Make sense? All right. One more little thing, and I'll explain why this is the case in a few minutes here. Somewhere in this video, you want to have a meter stick. It doesn't matter whether it's straight or whether it's at an angle like this. Okay, it doesn't matter where it is, but you've got to have a meter stick there. And what you want to make sure of when you're performing this collision between these 2 baseballs is that this meter stick does not get in the way of the collision. You don't want the balls to hit the meter stick until at least a couple of seconds after the collision has taken place, so that you ensure that you have enough data both before and after. You don't want the meter stick to get in the way. You also don't want the legs of a desk or something else to get in the way until at least a couple of seconds after the collision has taken place. All right, that's essentially it. Now, how are we going to use this software? You're going to take that video, by the way, and you're going to email it to yourself. You're going to record while you're doing this activity the mass of object 1 and the mass of object 2. Now, these are baseballs. These are cheap $4 baseballs from Walmart. The masses should theoretically be pretty close to the same, but the quality control on a $4 baseball is probably not the same as the quality control on a professional baseball that costs more than $4. So measure the mass. Don't assume the second one is going to be the same. It will be close, but it's probably not going to be exactly the same. Get both masses. Email the video to yourself, and then log on to a laptop computer, not a Chromebook, but a laptop computer. Log into your email and save that video to the desktop of your computer. Then go into the software program that we call Tracker. There should be a link to it on the desktop. And click this little tab up here which says Open. This, by the way, these instructions, by the way, are what are outlined in those instruction manuals that you're going to get as a group here in a few minutes. So click on this, this tab that says Open, and then you're going to open the video file that you want to analyze. Find it on your desktop, open it. Should look something like this now. Now you have to insert what we call a frame of reference. So you're going to click on this little button right here. It's for frame of reference. We have to tell the computer where to measure the position that it's going to measure from. Do I measure it from the right side of the screen or the left side of the screen? From the bottom, from the top? Tell it where to measure it from. It doesn't matter where you place that frame of reference. If you want to place it somewhere convenient, go ahead. If you want to place it anywhere in a random place, it'll work, as long as the frame of reference doesn't change throughout this activity. So place the frame of reference somewhere. Then you want to click on the Tracks button up here, and then you want to click on the New button, then the Calibration Tools button, then a calibration stick. Basically what we're doing in this step is to tell the computer what a meter is. It doesn't know. It's trying to tell you the velocity of this ball in meters per second, but it needs to know what a meter is to be able to measure the velocity in meters per second. So tell it what a meter is. Click on Calibration Stick, and then with your blue calibration stick, trace over the meter stick. Now you notice that I haven't traced over the full meter stick. The reason I haven't done that is because I noticed when I collected my video that not all of the meter stick was in my video. I missed part of it. Oops. It's not a big deal because my calibration stick, I can adjust the length. I made it 30 centimeters. Because it was 30 centimeters, I only made it partly the length of the meter stick. Make sense? You can make it whatever you want. If you've got the full meter stick in the video, make it a meter, 100 centimeters. If you've got only part of the meter stick, then make it 30, 20, 50, 70 centimeters, whatever you want, as long as you specify correctly what it is. So what have we done? We've imported the video, we've created a frame of reference, and we've told the software program Tracker what a meter is. Now we got to create our objects in the software program. The software program it doesn't understand where the objects are without you telling the software program where the objects are. So we've got to create a point mass for each of the objects. We've got two objects here. In the video that I have here, I've got two orange hockey balls. Okay, you're going to have two white baseballs. Create two objects, object 1 and object 2, so that we can represent the motion of both of these things. You can see that that's up there now, mass A and mass B. Which one is which? It doesn't matter. Make sure you understand though. Okay, this one could be A, this one could be B, it could be vice versa. It doesn't really matter as long as you make sure that you know which one is object A and you know which one is object B. You can take a Sharpie and write on the baseball if you want, okay, if that's helpful to you, whatever it takes to recognize which one is object A and which one is object B. Now what you're going to do is actually start collecting data. You're going to click on object A or on object B, probably object A first, obviously. And then you just scroll down here until just before the collision has taken place. You can see in the corner of this video here, my hand is in that. We don't want to start collecting data yet, so scroll down on the video until my hand has left that ball. Then you're going to start collecting data for it. Does that make sense? You've clicked on object A. Let's say that this is object A. You've scrolled down here until my hand has left the ball, and then you're going to start collecting data. You're going to start collecting data by pressing the Shift key and clicking on that ball. So Shift, click. That's going to put a little square in that position. And then the computer program will automatically move forward one frame in the video. Then you're going to do the same thing again. Shift click, it's going to automatically move forward one frame. Shift click, it's going to automatically move forward one frame. Shift click, and so on. They're going to collide probably somewhere around here. Well, then it's going to go off over here. Shift click, shift click, shift click for object A before and after the collision takes place. Then do the same thing for object B. Click on object B up here, shift click, shift click, shift click, shift click, and so on for object B before and after the collision takes place. So far, so good? Now it's time to actually get the data into a spreadsheet so that we can do something with it. Down here in the bottom right-hand corner, you're going to see your data. There's going to be one table displayed, and it's going to say either mass A or mass B beside that table. Click on mass A, then say Control A. Control A highlights all of this data. Control C copies that data. Go into your spreadsheet and go Control V, which will paste all that data into a spreadsheet. Then click on mass B. Control A, Control C, and Control V in your spreadsheet to paste all that data in your spreadsheet. Now, this software is done. You're now working in Google Sheets. You've got time and position X and position Y, both initial and final, for object A and object B. You've got all the data you need in one spreadsheet. Make sense? Now, what are we going to do as far as data goes? Well, you got to record your masses, of course. By the way, this template is already copied for you on Google Classroom. The only thing you need to do is enter everything and delete everything that's in purple, some instructions that are in purple. Enter the masses, which you've already got recorded. You're just going to record them into your Google Doc. Then you got to record the X and Y components of initial and final velocity of object 1 and object 2. How are we going to get those numbers? I'll tell you what, you're going to plot what amounts to 8 graphs. Position and time graphs. When you plot a position and time graph for X component, we'll say object number 1, X component, it may look something like this. It may look something like this. It may look something like this. Bottom line is you should have 2 distinct lines. One of those lines will correspond to the initial velocity, and the second line will correspond to the final velocity. Now, depending upon your frame of reference, I can't predict what it's going to look like, this, or something else. I can predict it's going to be 2 straight lines, but what those straight lines are going to look like, that depends upon what your frame of reference looks like, and upon what your collision looks like. So, object X, object 1, I should say, object 1, X component, might look something like this. We're going to say object 2, X component, is going to look something like that. We're going to say object 1, Y component, object 2, Y component, again, they're going to look something similar. You're going to have 2 distinct straight lines, 2 distinct velocities. That's 4 graphs. I said you have to, in essence, plot 8 graphs. Well, we kind of got to split these up, right? We've got to split up into object 1, X component, initial, object 1, X component, final, so that we can calculate the slope on Google Sheets and get the velocity. Make sense? So this becomes 2 graphs. Then you're going to split this one up to become 2 graphs, initial and final. same deal here, and same deal here. The good news is, again, is that you don't have to plot all 8 of these graphs. If you've got 4 people in your group, then one person can do this, one person can do this, and so on. It ends up not being an onerous amount of work at all. Yep. One collision only if the collision works well. Okay, if you find that it hits the meter stick right after the collision, you've got to do it again. If you find that one of the balls stops right away after the collision, you got to do it again. You got to have a good collision, but if you do, then one collision suffices, yes. Listen, once you get all these values, plug them into your table. This is your data. I don't need to see these graphs in your write-up. I need to see the numbers from those graphs in your table right here. This is data. Your analysis would be your calculation of momentum. Initial momentum, x component. We're going to say M1 V1 I x component plus M2 V2 initial x component. Final momentum, P final x component, M1 V1 final x component plus M2 V2 F x component, and so on. Okay? Do that here, and so on. Percent difference calculation. This is where a few of you made a mistake on your last lab. It's actual minus theoretical over theoretical. Or in other words, final minus initial over initial times 100. You're going to repeat that process down there for the y component. Conclusion, was momentum conserved in the x component? Yes or no? Was momentum conserved in the y component? Yes or no? And then how do you know? Sources of error, make sure you don't forget your suggestions for improvement.